Good morning. Today we're going to cover the fluid elements, which is the last domain that we still have to cover. And next lecture, we're going to start combining these different domains and look into more complex systems. So as we presented in the introduction, the through variable of a fluid element is the volume flow rate, and the across variable is pressure. So we're going to have different types of elements. We're going to have the fluid inerter, and the fluid inerter is equivalent to what the inductor is for an electrical system. Then we have the fluid capacitor, and for that we're going to have different types of capacitors. We can have just pure fluid compression. We can have a container that is flexible and there is going to be a difference in pressure. Or we can have a gravity head like what we would have in an overhead tank. And for the dissipating element, we're going to have a fluid resistor, which can be in the form of valves, or perhaps we can have just the pure resistance of the pipes on the fluid. So we're going to start with the fluid inerter, and as we said, volume flow rate is our through variable, and pressure is going to be the across variable. Now, what is a fluid inerter? Fluid inerter is what happens in pipes. In general, we're going to have a long pipe where when we make a change in flow, when we modify the flow that is happening within that pipe, there is going to be an increase in volume, in pressure. And that increase in pressure can affect our system. It will carry kinetic energy that is going to be stored in the pipes, and that can actually cause problems with our system. Now, I don't know if you live in a house, especially houses like mine is like that, where there is a long pipe that connects the water tank to the faucets in the bathroom. And whenever we open and close especially the hot water, there is going to be a very, very strong and loud noise. And that loud noise is what we described as water hammer, and that's kind of the phrase that is used commonly. Now, water hammer can be dangerous in pipes, and believe me, it can make a very, very loud noise. And what happens is that as you change the flow that is passing through the pipe, there is always some air trapped in the pipe, and the water would carry inertia. It's going to carry that momentum through its flow. And when there is a sudden change of the flow, then that inertia will compact on the air, and it will increase the pressure in that trapped air inside the pipes. And that trapped air and that increase in pressure is what causes the loud noise. It is a common problem in hydroelectric plants when you have the turbine at the bottom. So you have perhaps a stream where you collect the water, and then that water flows towards the turbine. And if you don't control the flow precisely, it can damage the turbine, and it can be very, very dangerous. So there are controllers that ensure that the way that the valves are being closed or opened are regulated. So inertia in the inerter is an element in the fluid elements, and it's something that we have to consider. In general, when we have a long length of pipe where this inertia of the water can increase considerably the pressure in the air that is trapped inside the pipes. Now, the equation that we're going to use for inertance is this one here, where the difference in pressure, and that would be P2 minus P1, is going to be equal to the fluid inertance times the time derivative of the volume flow rate. And IF, the fluid inertance, is going to be equal to alpha, which is a constant, and alpha can vary depending on the type of flow that we have and the type of a pipe that we have. Is equal to 1 when the fluid has a uniform velocity distribution, so it just flows. But if we have a circular pipe, where if you have the circular pipe, then there is going to be a profile of velocity which is going to be parabolic, so there is going to be friction on the walls of the pipe, so there is going to be greater velocity in the middle than near the border with the pipe. So in that case, alpha is going to be equal to 2. Then we have rho, which is the density of the fluid, delta x, which is the length of the pipe, and A, which is the cross-section area of the pipe. So the constitutive equation that we're going to use is going to be this one, where we have the difference in pressure is going to be equal to the fluid inertance times the time derivative of the volume flow rate. Sometimes I'm just going to refer to flow rate to shorten that. Now, this is going to be an energy storage element. There is kinetic energy, which is associated to this element. So it's a type T, and this would be equivalent to what we have in a spring or in an inerter. So the volume flow rate is going to be the state variable of the inerter. So the next element is the capacitors, and we can have different types of capacitors. We still have volume flow rate as our through variable and pressure as a cross variable. The equation for capacitance, and this is going to be the same for all of them, is going to be given by this equation, and this is the flow rate is going to be equal to the fluid capacitance times the time derivative of the pressure with respect to time. And this is an example of pure fluid compression. So there is going to be flow going into the tank, and this is a rigid tank, so the pressure inside the tank is going to increase. We're going to have a constant volume, and the pressure outside is going to be different. So if we have liquid and that is compressible, then we're going to use this equation to determine the fluid capacitance, where the controlled volume, which in this case would be the volume of the tank, divided by the bulk modulus, and the bulk modulus is the resistance of the fluid to compression, will give us the fluid capacitance. For an isothermal system, where we're going to keep a constant temperature in a slow process, and this is for gases, the fluid capacitance will be given as the ratio of volume to pressure. And these one, as well as the adiabatic systems, where in the adiabatic system we have zero heat transfer. It's going to be a fast process for a gas, and again we have a controlled volume V. In this case, the relationship will give us a fluid capacitance, that is the controlled volume divided by K times P, where K is the ratio of the specific heats and the Cp over Cv. Now, these two cases, isothermal and adiabatic, we're not going to see them in detail. We're going to consider cases where we're compressing a particular fluid, and we're going to use the fluid capacitance, which is going to be determined due to the bulk modulus of how that particular fluid is compressing. So in terms of the through and across variables, we're going to have that the volume flow rate is going to be equal to the fluid capacitance times the time derivative of pressure. Now, this is going to be an energy storage element. We're going to store potential energy. This is going to be associated to pressure, which is the type or the across variable. So this is going to be a type A element. So pressure is going to be the state variable that will be introduced by a fluid capacitor. So in the case of inertance, we're going to introduce flow rate in the case, and that would be our state variable. In the case of a fluid capacitor, we're going to introduce pressure as our as the state variable that is defined by that particular element. Now, there is other ways in which we can have a fluid capacitor. It would be, for example, the case of a flexible container. In the case of a flexible container, we're going to have two parts. One that is going to be associated to the mechanical model of the flexibility of the container, and that will lead to a fluid capacitance that is related to the elasticity of the container, and that is going to be equal to the square of the area of the, in this case, of the container, and that we're just assuming that this is a cross-section area that that we're referring to. And then we're going to also include the fluid capacitance related to the bulk modulus. Now, in class on Wednesday, we're actually going to derive this equation. So we're going to start working and combining two different domains, the mechanical domain with the fluid domain, and we're going to derive this relationship that we have here. And again, the constitutive equation is going to be this one, and this is still an energy storage element where pressure is the state variable that is associated to this element. And perhaps the most common type of fluid capacitors is the gravity head. And in the gravity head, we're going to have like what we have in overhead tanks. we're going to have a difference of pressure between most likely the atmospheric pressure and the pressure at the bottom of the tank where we're going to have the outlets. So this is a common problem with overhead tanks. We're going to consider incompressible fluids, and the column made by the fluid, in this case H, could be used as a state variable, or the pressure difference that we're going to have between the atmospheric pressure and the pressure at the bottom of the fluid column. The fluid capacitance, in this case, can be derived in terms of the cross-section area of the tank divided by rho, which is the density of the fluid, times gravity. And the constitutive equation is the same one. The flow rate is going to be equal to the fluid capacitance times the time derivative of pressure. And this is again a type A element where pressure is the state variable. And finally, we have the fluid resistor. And with the fluid resistor, we're going to have again, we're going to have a drop in pressure that is going to happen at 2 points or 2 extremes of our element, and we still maintain the same flow rate passing through the element. And the way that we're going to represent the resistance, and it can be perhaps in the form of a valve, is going to be that the drop in pressure, or the change in pressure, is going to be equal to Rf, which is the fluid resistance times the volume flow rate. And that would be the linear representation. It is possible that we could have a nonlinear representation, and this is part of a more complex model of our system, which is going to be given by this relationship, and again, where Kr is an equivalent of the fluid resistance, and then n q to the n, that would make it nonlinear. Now, in many cases, that n and that k are going to be values that would have to be determined experimentally to determine what is the proper value of these parameters. Now, for what we're going to do in this course, unless you want to include a nonlinear term in your project, we're going to consider the linear case. Eventually, it's part 3, but we're going to see it perhaps in like a month. We're going to introduce the cases of nonlinear parameters, something nonlinearities, like in this case, and we're going to look at 2 potential solutions. So that would be a moment in which we can introduce the nonlinear model of a fluid resistor. Now, another type of fluid resistor is what happens in the pipes. As we mentioned before, when we're talking about laminar flow and what happened with the profile of circular pipes, that we're going to have a parabolic flow, well, there is going to be resistance of the walls of the pipe on the fluid. So if we had a circular pipe, we can determine the resistance in this form. It's going to be 128 times mu, which is the viscosity of the fluid, times L, which is the length of the pipe, divided by pi times the diameter of the pi to the 4th. And if we had a rectangular pipe, then the evaluation of the fluid resistance is going to be 12 times mu, again is the absolute viscosity of the fluid, times the length of the pipe divided by W times B cubic, where W and B are the width and the height of the rectangular pipe, with the width being greater than the height. So once you establish the numerical value of the fluid resistance, then you can substitute it into the constitutive equation, and now we have that the difference in pressure is going to be equal to the fluid resistance times the flow rate, or the volume flow rate. This element is not going to introduce a state variable. It's a dissipating element. It's not going to store any energy. So this is going to be just an element that will be considered in our systems, but will not introduce a state variable. So we're going to see a couple of examples. We're going to do one example recorded, which is this one here, and then on Wednesday we're going to cover another example of an overhead tank that contains 3 outputs, also we're going to solve the problem that I mentioned before of the flexible tank and how we can determine that relationship. And this is the relationship of the fluid capacitance with the flexible container. So what we're trying to demonstrate is that the fluid capacitance is going to be equivalent to the addition of the elastic fluid capacitance, which is going to be a mechanical relationship, plus the fluid capacitance due to the compression of the fluid. So with that, we concluded basically all the different domains. We introduced the single elements for each domain. So we're going to start now working and developing more complex models. But before we go into what I would call hybrid systems, where we combine the different domains, I just want to summarize a few concepts that we learned in these lectures, and the relationships and analogies that we have among the different domains. So in this course, or so far in this chapter, what we introduced was the concept of the across variable and through variable, and for each domain we're going to have one through variable and one across variable. The through variable is going to remain unchanged through the element, whereas the across variable will be changing across the element. Now, these are the equations, the constitutive equations that were derived for each of the elements. And you can see that these equations are very, very similar. I remember a long time ago, I was determining or looking into when the equations were derived, and sometimes there is like 100-year or even a 200-year period between when it was derived for one domain and when it was derived for the other domain. Now, the concept itself, based on across and through variables, is very similar. For the type T elements, we have on the left-hand side the time derivative of the T element, and on the right-hand side we're going to have a coefficient, whether it's just a simple coefficient or the inverse of the coefficient times the across variable. For the mass elements, the type A elements, we're going to have the through variable that is going to be equal to a coefficient times the time derivative of the cross variable with respect to time. And you can see that in every case, we're going to have a coefficient. In this case, all of them are linear coefficients that are multiplying the derivative or the differential term. And finally, we have the dissipating elements. And on the left-hand side, again, I wrote all the through variables. And on the right-hand side, we have the across variables. And we can see that in every case, we have a linear relationship between the two variables. It could be just a relationship like that, the coefficient, or the inverse of that coefficient. So for linear models, which in this case, so far we have considered that the elements can be modeled with linear equations, and we're going to see later on that we can change that and change how these coefficients are derived. Some of them can be a function of time that are changing over time, or perhaps they're non-linear. So those cases will be seen later in the course. But for the moment, we're just considering that all these coefficients are constants and that we're going to store them in this A matrix that will represent the system, the matrix of the design parameters of the system. Now, sometimes, and this is something that my former professor of this course, when I took this course, it was called electromechanical systems. He used to say, mention it quite often, and kind of made us think outside the box. And he would say, well, what do you think if we were able to implement what we are learning in other domains, completely different, outside engineering? Think about social sciences, think about economics, think about anything like the, I don't know, housing market, whatever, like whatever the topic is about, and think about some similarities that we have with the different analogies that we've seen so far. So, for example, social sciences, society in general. Before we go into the topic of immigration that I have here, what do you think would be the equivalent of a capacitor in society? Perhaps cities. Cities are an example of how people get together, right, and form this huge capacitor. Now, immigration, it would be an example of a particular element on social sciences, where people emigrate to other places. Could be people within the same country going into cities, going into these large capacitors, and there is going to be the will of going and moving to the large cities, and there is going to be resistance from sometimes the government, sometimes from social groups that are not going to allow people to move as easy. And I mean, that's common, especially nowadays in some countries. I don't want to get political, but that immigration can be a problem, especially for people moving from other countries. So if we were considering the through and across variable, well, migrant population, the population people are not going to change, is going to be the same. The people that are moving are those people that are going, and the across variable would be for each individual, there is going to be a different desire, different opportunities, different things that they're looking for, and that would be the equivalent of an across variable. So as we can see, or as we can kind of in very abstract manner, we can think about the different elements already. We can think about cities. We can think about the resistance of social groups towards immigration. But at the same time, there is going to be that inertia, that willing of the immigrant to move into another country to have these new opportunities. Now, what about in economics? What about the financial sector? Think about what would be the equivalent of a capacitor. Banks. Banks would be a place where we're going to store energy, and that is going to be like, same with cities, we have energy, lots of people and diversity. Same is going to be with in the financial sector. We're going to have banks, we're going to have the stock market, where we're going to store all these eventually is going to be our cross variable, which is going to be money, trades, bits, right? Whereas the through variable is going to be the volume, the volume that we're going to have in terms of securities, stocks that are going to remain those, but there is going to be a desire to buy, and then the prices can go up or can go down. So if we think about the financial sector, well, banks and the stock markets are examples of capacitors. And in the case of resistance, well, there's going to be regulations, and they're very well needed to regulate. Otherwise, it's a very wild domain in terms of how the trades are made and the bits are made. They have to be highly regulated. And of course, there is going to be the inertia of people trying to get particular commodities or particular traits that they want to have. And sometimes that can cause also too much of that inertia can also create problems, because if there is too many people bidding towards something, then that will saturate the market. So I don't want to go beyond that. This is just kind of an exercise that sometimes we do as engineers to try to think outside of the box and see other domains in a certain way. But I feel like even though we're not going to develop mathematical models to represent these domains, but I find it always a good exercise that we can actually perceive these domains in a certain way, and the similarities that we're going to have with the domains that we usually work on in engineering, like mechanical, electrical, fluid, and thermal. So at this point, we're going to talk a little bit on modeling and the need of modeling. And in your project, you have a design project, and there are many design projects that would require a strong model before we actually build a prototype. There are going to be models or even cases where we cannot even build a prototype. An example would be, or the actual scale prototype, like for example, an aircraft or a shuttle, right? If you go to space, I mean, you're not going to create a prototype that you're going to launch to test. Yeah, your test is going to be kind of once you build that prototype, that's your final product. There are going to be other products where you can test and you can improve, right? And you can even destroy it and then redesign. But in general, that it's expensive. Just building a prototype that we're going to use to test our design is expensive. So modeling and simulation will give you this opportunity of building, creating a model of your system, of your design, and gather information of what is going to be the response of the system based on a set of parameters that we're going to consider. And these are parameters part of your own design. So at the beginning, we always have to define what are going to be the boundaries of our scope. And you try to minimize all the redundancy. I know that there are going to be multiple factors that can affect our system, but we're just going to focus on the main factors. Then we're going to develop our model, and we're going to simulate our model. Sometimes, and eventually the results of the model were going to give us information. Sometimes we can change our model. We can change the model that we're going to simulate. We can change parameters, right? So we still maintain the same model, but we can change the value of the parameters because we saw that the results that we're obtaining were not correct, and we wanted a different response to our system. So we can modify those parameters, or in some cases, you might want to change the model on its own and start adding more elements or making changes to your design and adding other elements to your design that eventually will affect your model. Once you are happy with that, then you can always go back to the original concept of your design and verify whether or not it's meeting the purpose. And if it does, then now you have at least a proof that your design can work. So you can proceed with building your prototype. You can build your prototype and check, of course, test your prototype and look at what the response is. So this is kind of an intermediate step in the design, but as I said, there are going to be some projects where you cannot build a simple prototype. The most you can do for, I don't know, aircraft design is to test in a wind tunnel wings and the fuselage and things like that. But I mean, there are so many other things, other factors that you're not testing, so that you cannot test physically unless you are up in the air or in space. And that's why you want to include these elements in a model and simulate. The way that we're modeling, and we mentioned this when we covered this example of the room that is being heated, is that the way that we solved this problem was fairly straightforward. We just considered that the temperature inside the room was constant, and the temperature outside the walls was the ambient temperature. But we can go beyond that, and we can start developing a more accurate or representative model by including radiation within the room and determine what would be the temperature on each side of the walls, or the gradients that we're going to have inside the room. And then outside the room, we assumed, as I said, that the temperature on the walls and on the roof was the same as the ambient temperature, but most likely we're going to have a different temperature, and we would have to consider convection, how that heat is being transferred to the ambient, and what is the loss. So there are many things that we can include. We can always revisit our models, revisit our simulations, and gain insight with as we go, right? So it doesn't cost anything. It's just a change in parameters sometimes, or just a change in the design and change in the model that we're creating. And again, the more complex we make it, the more insights we get from the system. But again, we'll never be able to replicate what the real system would give us. This modeling and simulation is an approximation, and we keep it simple. There's not too much that we can do in some cases, but the more complex that we do it, the closer we get to reality. But always keep in mind that we're approximating what a real system, how a real system would respond. So these are some remarks that and comparisons that we can also make. The first one is that we're going to consider, for example, the case of a spring and a mass system. There is not a unique way in which we can model a system. We saw it with even state space representation. There are different ways in which we can approach it. But even the state space is not the only method that we can follow. So we can, for the case of the mass and spring, we identify the elements, and we can select the variables. We can select the through and across variables, or we can use the displacement and the velocity, and this could be another set of state variables. Or we can represent or we can approach the model in a different way. So if we were using the through and across variables, then we would develop our state equations in this form, where we're going to have the time derivative of the velocity and the time derivative of the force that come from our two energy storage elements. But also we can represent that with a second order differential equation that only involves the displacement and the velocity, or in this case, using Newton's second law, would be the acceleration. Now, as we develop our equations, if it's necessary to eliminate redundant variables, so if there was friction, or that would be an additional variable that we would eliminate using the through and across variable representation. Then if there are coefficients that are nonlinear, we could linearize them, and that's something that we're going to see later in the course. And then we're going to write the model. Now we can write it in the terms of state space, and that would be our traditional way of representing our state space model. Or perhaps we can write it in terms of a transfer function. And perhaps many of you who already took what course is MSE 381, I believe, you're already exposed to transfer functions, and this is going to be another way in which you can determine what is going to be the response of the system. And in a transfer function, you're going to have a relationship between the input and the output, which is going to be related by this equation, or this relation that is going to be the transfer function. So both equations eventually should give you exactly the same response, the same results. It's just the approach that is going to be different in every case. So there are problems that might be easier to manage using the transfer functions, especially if you have first or second order state variables. I usually employ them with larger energy storage elements, transfer functions you can always use MATLAB to determine, but State variables, I don't know, it gives you a good perspective of what is happening with the system, and as we're going to see later, we can even create a graphical representation of the problem. So this is these are two different ways of approaching a problem, and they are completely different in terms of the math, but both of them are valid methods of identifying what the output of the system is going to be, what the response of the system is going to be. Now, there are going to be a couple of properties that have to hold for a state model. The first property is that if we had a state vector that we defined x that is evaluated at t naught, so at the beginning, and we have an input that we know that goes from t naught all the way to tf, and we know how that input is going to be changing within that interval of time, then this is the only thing that we need. And of course, we need the initial conditions of our state vector, and this is defined by these. So if we know the initial conditions of the state vector, and we know what is going to be the input through a period of time, then we can simulate our model and determine how the state vector is going to be changing throughout that period of time. And that's going to be just from t naught to tf, which is the period of our input. Now, in this case, we're going to represent the state vector in this form. I'm not writing the common equation of x dot equals a times x and so on. This is a kind of a generic way to write it, where function g basically represents what would be the solution to that differential equation that we're deriving. And this is just a way to do it. So when you have nonlinear terms, you have this equation. So if you had nonlinear terms within your parameters, then you cannot write the equation that we've been using so far, because there are going to be all these nonlinear terms inside a coefficient matrix, so you cannot evaluate them. So we would have to just keep all the state equations as they are, and all together are they're all put together in this function g, and that's how commonly are represented. So in general, dynamic system is causal, and that is that the determination of future states requires all the inputs up to the future time. And a way to describe this is that imagine that our goal is you have a coffee cup, and you leave this coffee outside your house or your apartment, and your goal is to see how the temperature of the coffee is going to change over time. And you know what is the temperature through the day, right? And you want to just finish at 5 o'clock in the afternoon, from the moment that you put it outside all the way to 5 o'clock in the afternoon. So if you know the initial temperature of the coffee, and you know how the weather and the temperature outside and the current of wind, because that is going to change the convection that is happening with heat transfer is. So if you have that information, then you can simulate the model, and you can see how the temperature of the coffee is going to change over time. Now, what we need is we just need to know we need to know all the inputs. We need to know what the temperature is going to be until 5 o'clock in the afternoon to output the temperature of the coffee. Now, the system is non-anticipative. That is that any input beyond TF are not needed to determine what the temperature is going to be at 5 o'clock in the afternoon. We don't care what the day after is going, the temperature the day after, 2 weeks after is going to be. What we need to know is the temperature from the moment that we put the coffee outside all the way to the 5 o'clock, the temperature, the ambient temperature, or and the same is going to be if the coefficient of convection perhaps it's going to be constant, and we're going to have a constant value, but if it's changing, then it becomes a time-dependent parameter. So that would be the other element that we would have to know in order to create our simulation. And the second property states that the state at, and we know what would be the response of our state vector, and we know the input at any time, and this is going to be from T naught all the way to TF, and that's for both. So once you solve for the state vector and you know the input, then with that information, we can determine what is going to be the response of the system. And again, we're going to use, rather than using the matrices C times X plus D times U, if we had nonlinear terms, then you have to express that in a different way. And this is kind of the generic way of representing that. So we're going to have this function that allows us to map the state vector and the inputs into the outputs. And well, the transformation H has no memory, so it depends completely with depends on the value of the state and the value of our input vectors. So in summary, what we said is that a state vector is the minimal set of variables that completely determines the dynamic state of a system. So a state variable cannot be expressed as a linear combination of the remaining state variables. So this is important to create that minimal set. If you have, for example, say that you have gears. A gear, right, can be modeled as an inertia element that is turning. And then you have another gear, and this is also another inertia element. Now, if these two gears are in mesh, right, it's not like we're going to have two energy storage elements. Perhaps we have one, right? Perhaps we have one, and the other one is going to be a function of the other one. And it's going to be the gear ratio that will determine what would be the angular velocity and the torque that we're going to have on the other gear. So now I was saying that perhaps because it is possible that that gear is connected directly to a motor and the shaft is rigid shaft. So in that case, the voltage that we are applying to the motor might be the state variable, and the angular velocity that we're going to have with the gear is not going to be, but this is something that we're going to see later when we start combining hybrid systems. But what I want to kind of point out is that, yeah, even though you're able to count all the energy storage elements, you have to make sure that they're independent. Okay, perhaps there is going to be a dependency that is easy to see, like in the case of two gears that are in mesh. or two springs that are connected in series or in parallel, or two masses that are attached. That's the same as a whole mass, right? A unique mass. So that's something that you have to keep in mind. Then the state vector is not unique. There is many choices that you can have. You can have the what we defined as the mathematical approach, or you can have the physical approach based on the across and through variables, or you can have the flow and effort approach. So there is different ways in which you can model your system. The output or the response of the system can be completely determined from any choice of state variables that we make. So we're going to see, I'm trying to make a couple of examples that the method is going to be completely different. Like we're using the physical approach with the through and across, and we can use the mathematical approach. And the state variables are completely different. In one case, we have forces and velocities. On the other case, we have displacements and velocities. But the response of the systems is going to be the same. And then if we find the response of the variables that we're interested in, we're going to see that they're equivalent. The graphs are going to look alike. Perhaps we can do the same between use this a space state representation using the across and through variables, and using transfer functions, and the result of the outputs is going to be the same. Just the way that we're going to reach that is going to be different. And the order of the system is equivalent to the number of state variables, which is the number of independent energy storage elements that we have. So in addition to that, models can be time invariant. In this case, we're going to have differential equations that are going to have constant coefficients, or they can be time variant, where the equations will have coefficients that are going to be changing with respect to time. We talk about, for instance, the case of the coffee mug that is left outside. Well, we have convection of how the heat of the coffee is being transferred to the ambient, but I mean, wind can change, and that H, that coefficient can change, and we can have a linear coefficients, or we can have nonlinear coefficients, and this is something that we're going to cover in part 3. But still, like I'm moving some of the parts, so this is going to be like a month from now when we see that. And perhaps a spring that so far we have used Hooke's law, but what we're going to see is that even a spring in general, the spring it doesn't behave in a linear form. It behaves more as a cubic. Like if you were going to plot the effect on compressing the spring and the force that you're obtaining based on the displacement, you're going to see that it's nonlinear. So the way that you would have to represent that K, now it's a nonlinear term, and so it is different. So now, so far we've seen linear cases, and we're going to continue with that until we start looking into problems of nonlinearity and how we're going to solve those problems with approximations or more accurate results, but that will come later. Now, if we want to check if our system is linear or not, we can apply the concept or the principle of superposition. And it says, and basically it says that if you have an output at time equals t1 of your system, and that happens when you have an input at t1, sorry, and you have another output at t2, which happens at evaluate the input at T2, then if you add these two outputs that are being multiplied by a real constant alpha 1 and alpha 2, this output must occur at this particular input, which is going to be associated to the two real constants. So this is just kind of the theoretical representation of linearity. We're going to have linearity when we have linear coefficients in our matrices. And so a linear case is something that can be structured with in a matrix form, where we're going to have A, B, C, and D, and we're going to have all these coefficients that are constants inside these matrices, and we can evaluate what the response of the system is. Now, if those constants or those parameters are no longer constants, and then we're going to write that in a different form and with the G and the H, and we're going to see how we're going to solve for that, but that will come later. And finally, this is just a comparison between the state models and transfer functions. So the transfer functions are going to be input-output models, which is different from what you get with the state space models, that you go through the whole process of how the state vectors are changing. With the transfer functions, we're going to develop a differential equation that could be could be higher than first order, whereas our state equations, all of them are ordinary differential equations. So we're going to have our transfer function that will give us, for the mapping, will allow us to map what would be the response of a system for a particular input that we provide to the system.